Conservation of momentum allows us to solve some pretty complex problems without too much effort, which is why it's such a cool thing to use. So let's do an example problem. A 10 gram bullet moving horizontally at 400 meters per second penetrates a 3 kilogram wood block resting on a frictionless surface. A. If the block is moving at 0.5 meters per second immediately after the bullet emerges from the other side of the block, how fast is the bullet moving? Or B. If the bullet does not emerge from the block, how fast will the block be moving? Alright, so there's two different cases, two entirely different problems to work here. I like pictures. Before and after pictures are to me the only way to do these problems. So before, after. And you have to define what's the before and what's the after. Well, this is before the bullet hits the block and after the bullet emerges from the block. So initially I have a block and it tells me it's 3 kilograms and I have a bullet. And the bullet is 10 grams, which is 0.01 grams. And it's moving this way. It says 400 meters per second. This thing is at rest. That's my before picture. Now for case A, it says immediately after the bullet emerges from the other side of the block. So the block is still here, but now we have the bullet over here and it's moving this direction. I'm assuming it says it's immediately after emerging from the block. It's still got a mass of 0.01 grams. I guess we're assuming none of the mass got stuck in the block, and the block is going to be moving as well with some velocity v. And what we're supposed to figure out, oh, actually it tells us that, right? It tells us that this v is 0.5 meters per second. What we're supposed to figure out is how fast that bullet's going. So this is not as complicated as it looks. Okay, all I have to do is realize that the total momentum before is equal to the total momentum after. If I use that, then I'll be good to go. So let's find the total initial momentum. It's just the momentum of the bullet, MAVA to start with, plus the momentum of the block, MBVB, right? That's object A, object B. And so that's 0.01 times 400 plus 0. Why 0? Well, an object at rest has no momentum. So this is just 4 kilogram meters per second. Okay? Remember, this is 0.01 kilograms because it's 10 grams. So 4 kilogram meters per second is my starting momentum. Over here, what's my final momentum? Well, it has to be this. So 4 kilogram meters per second is equal to 3 kilograms times 0.5 meters per second plus the mass of this thing, 0.01, times its velocity, v. I don't know what its velocity is. I'm looking for it. So 4 is equal to 1.5 plus 0.01 v. I can subtract that over. I get 2.5 equals 0.01 v. Divide both sides by 0.01, divide by 0.01, and I get a velocity of 250 meters per second. So when this thing hits the block, it goes all the way through it and comes out the other side. Because of that, now it's only moving at 250 meters per second. It slowed down going through the block, and it transferred some momentum to the block. So now the block is moving to the right, the bullet is moving to the right, but slower. Okay, so the total momentum before and the total momentum after are the same. Question B, if the bullet does not emerge from the block, how fast will the block be moving? So we still have all the same original information. So start this picture over, before and after, but now our after information is a little bit different. So I have a 10 gram bullet, which is really a 0.01 kilogram bullet, 0.01 kilograms, and it's moving this way at 400 meters per second. That didn't change. I have a 3 kilogram block sitting right here. That didn't change. It's at rest. However, it says afterwards the bullet is stuck in the block. Okay, and we'll come to that one in a minute. So before, I have 0.01 times 400 plus 0, which is still 4 kilogram meters per second. Now over here, these two things stuck together, which means my mass is not 3 kilograms anymore. It's 3.01 kilograms. I have a block of wood with a bullet in it. But I can consider that as one object. So now I have 3.01 times whatever velocity these two things have, right? Because if the bullet didn't come out of the block, the two things are stuck together. They're traveling with the same speed. So all I have to do is say 4 is equal to 3.01 v, divide both sides by 3.01, and we see that this thing has a velocity of about 1.3 meters per second. Let's go ahead and take a look at case C. And case C is, what if the bullet doesn't go through the block or hit the block? What if it bounces off the block and ricochets back the way it came at 100 meters per second? Okay. So I have my before picture just like before, and I have my initial momentum just like before. My total initial momentum is still 4 kilogram meters per second. But afterwards, I've got to pay attention to sign, because my block is still got a mass of 3 kilograms, but my bullet is now traveling the other direction. So this is 0.01 kilograms, and it says it bounces back at 100 meters per second. So it's going the other way. And so over here, what I have is my momentum over here is 0.01 times negative 100 plus 3 times however fast it's going, v. So I just assign that this direction is positive and this direction is negative. Now I have 4 kilogram meters per second is equal to negative 1 plus 3v. Well, if I add this over, I have 5 kilogram meters per second is equal to 3v, and I'm going to divide both sides of this by 3, and I see that v is equal to 1.66 meters per second. You'll notice that's faster than it's been in either of the other two cases. In the first case, where the bullet emerged from the block, it moved at half a meter per second afterwards. When the bullet got stuck in the block, it moved at 1.3 meters per second. But when the bullet bounces off the block, it moves at 1.66 meters per second. And that's because this thing underwent a greater change in momentum than any other time. So that means more momentum had to be transferred to this block. However much this one's momentum changed, so however much this thing's momentum increased. Okay? So the law of conservation of momentum does allow us to solve some pretty tricky problems without a whole bunch of effort.